is this is a 2,000 degree torch, and we're going to put it right here in my hand. And we're going to hold it there. You can see the red flare from the heat itself. And we've already been there long enough for the heat to start coming through if it was going to load the heat and bring it through to my hand. But what's going on here is that this particular compound physically does not have the density to absorb and hold heat. So it throws it back off to the atmosphere that's cooler than it is. And it does it very quickly, as fast as it comes into it. So one of the things that we want to also demonstrate is when I take the heat off and you see the die down of the red, then given a certain amount of seconds or so, about a minute or so, that was 2,000 degrees, and it was throwing it off constantly. And it did load a little bit right here, but then now we've been about 20-30 seconds, and I can put my hand into the powder and not burn my hand, and it's not hot. So 2,000 degrees, throwing it off, and then it unloads that heat exceptionally fast, and that's called emissivity. Not reflectivity, but emissivity. And that's what we're talking about. So Supertherm works on both angles, reflectivity and emissivity. And so that's why Supertherm is as effective as it is, because it does both sides. It's not just a reflector. That's why when it gets dirty, like after 18 years on a test roof that the Japanese have been testing with in western Kansas, after 18 years we only lost 8% of the effectiveness of it because of the emissivity part. It's dirty. It may not be able to reflect like it did in the beginning, but it still does not load heat. And that's why it continues to work. Not because of reflectivity, because of emissivity.